Hello, everybody. Welcome to the Modern Compilation Targets track. As I said, if you heard my intro earlier, this is a new track, which is kind of exciting. It's always fun to kind of mix things up a bit. We've got some really great talks coming up in this track. I'm going to actually intro them a bit throughout my talk, but I'm really here to talk about the modern platform and why languages are so important to everything we do now, and really highlight some of the things that are happening with compilers and languages, and what kind of things we're building and that you can build, and give you a flavor of why things are changing and what's going on, and why we're having this kind of track, and what kind of things we're going to be working on and building in the next few years. I'm an engineer at Docker in Cambridge, UK. I've been speaking and track hosting at QCon for quite a lot of years now. I have kind of broad interest I've been working a lot in security, so I kind of have a little bit of security bias sometimes, but system software, applications, and what's going on with applications, containers and things like that. You can find me everywhere as Justin Cormack, easy to find if you remember my name. Cambridge is, if you don't know Cambridge, this is just down the road from where I live. It's basically, Cambridge is a sort of tech village. It's kind of a fun place. So this is where, just over 50 years ago, quasars were discovered, not using these telescopes, but it's an interesting mix of the countryside and the high tech, which is always kind of fun. For a while, I was running the operating systems track at QCon, and then I kind of moved I did the language track in New York, and now I'm doing the modern compilation targets track, and it's like, well, why have I kind of moved this way? I don't know, I find it's not really a big change. These are both areas that I've been really, really interested in for a long time, and part of my interest in kind of new developments in operating systems has been around things we can do with programming languages and new programming languages, and the fact that, we've literally spent all this time for many, many decades building operating systems in C, and this is really a terrible idea, and we should have stopped doing that a long time ago. And there's loads of new developments going on with programming languages that in the operating system space and other areas that have been really, really fascinating. And a lot of the drivers for change are kind of similar in some ways. So some of the bits that I was talking about in operating systems a few years ago has sort of also made the changes in languages. So with languages and compilers and compilation targets, has anything really happened recently? I'd say yes, actually. A lot of things have happened. I'm going to talk a lot about performance because it's an area that I find is really important and really interesting, and I think that we underestimate the kind of drivers that performance has on what we do with computers, and it also affects all sorts of other things. Hardware is changing because of performance and the end of Moore's law and those kinds of reasons. Hardware is a thing that, as programmers, we sometimes ignore, but really hardware's changed a lot, and the programming languages that we used to use, there's a story, the thing that's saying that C was based on the PDP-11, which is not quite true, but it's kind of got a lot of semi-truth in it. But we're going to talk a lot in this track about different architectures like vectors and GPUs and FPGAs and things like that. These are, hardware is fundamentally changing, and programming languages are changing because of this, and how we use them is changing. We're also going to talk about tiny devices. I think, ARM ships 20 billion microcontrollers a year, and someone has to program these things, and this is a really interesting area, which we're going to talk about. And security. As I said, security is something that I've been working on quite a lot, and there's some real changes in security. Software is being attacked faster than ever, and programming languages can help us with this, which is kind of useful. I always give a little bit of history in my talks. This talk's probably got less history than most of my talks. Like the keynote before, I kind of got a fascination with bits of history. But the programming environment, we've had 3 really gigantically successful language projects: GCC, LLVM, and OpenJDK. And those are gigantic projects and have been immensely successful. GCC itself really witnessed the birth of commercial open source software. Cygnus, which is a company that most people have kind of forgotten about, was founded as Cygnus Your GNU Support, was what Cygnus stands for, because everyone loves recursive acronyms, especially back then. It was really the first commercial open source company, founded in 1989. It was acquired by Red Hat a little later than that. Their main business was building GCC ports for all the many hardware platforms that existed at the time. And they were so successful that most other commercial compiler vendors closed down over the years after that, because open source was immensely more efficient, because they could just add a little bit of back-end for your thing and use the same front-end for the compiler. LLVM was a university project originally, but was supported by Apple and later almost everyone in the ecosystem, and has become immensely successful and provided competition to GCC. And OpenJDK has really created the whole JVM ecosystem and has been immensely successful and really innovative in performance and so on. These projects have allowed a huge number of other languages to thrive. These started off as C, C++ compilers, but and JVM compilers, but actually, lots of languages like Rust, for example, use LLVM. Some languages build their own stuff, but these kind of huge projects have kind of made like proper high-performance compilers very accessible to all sorts of new projects and experimentation. So they've really kind of molded the kind of environment we're in. Performance is something that really I talk about a lot. One of my favorite quotes from a long, long time ago is: a supercomputer is a device for turning compute-bound problems into I/O-bound problems, which is one of the sort of historical things that you end up doing a lot of compute and then you run into other problems. But the big performance change that we've really seen in the last sort of 5 years is that I/O has actually got really, really fast. And cheap 25 gig Ethernet and 100 gig Ethernet have kind of changed the world. Since this was actually a forecast from a few years ago about network controllers. Amazon enormously invested in building out 25 gigabit Ethernet, which is what they use in all their new machines, and they created this whole market segment and made it really, really cheap. And almost all servers, I think the majority of servers shipping now have 25 or 100 gig Ethernet. This is like really fast compared to the sort of gigabit we were using like even just a decade ago. SSD, NVMe, NVDIMM, all these things, we got fast storage now, like really, really fast. Millions of I/O operations a second, which is like a huge change from hard drives, which would do 10 or 20 a few years ago. And we've got loads more CPU cores to drive these things, but clock speeds have not really gone up all that much. So we've had a few orders of magnitude performance improvement in I/O in our CPUs in the last few years. And even if you look at your laptop, like USB-C USB has gone from something that you would plug your mouse in and 20 years ago to something that runs at 10 gigabits or Thunderbolt and those types of things that are even faster than that. Back in the 2000s, we were interested in, there was the famous C10K problem. Can we have 10,000 connections to a server? We have people doing 10 million connections to a server now. These orders of magnitude change are really, really big, and they actually require high performance. Every CPU cycle counts. Even for just 10 gigabit Ethernet, you've only got 130 clock cycles per packet for a small packet. For 100 gig Ethernet, it's 13. You really can't do much work in that time. So there's a lot of optimization and performance that's really, really important for these things. And storage has gone through the same thing as networking, that we've got really, really fast storage, and we're ending up with flash storage and memory form factors and things like that, which are incredibly high performance compared to what we had before. So to drive all this stuff, there's a whole bunch of issues. First of all, power consumption is something that is really, really important to think about. And you know, data centers consume about 3% of all electricity we use, and it's growing. And that's a worrying trend. Some of the estimates suggest it might go up to like 10, 20%, which is just kind of scary if you think about the amount of energy that we need to produce to do that. While large cloud providers are more efficient than traditional data centers, a lot of their power is still fossil fuels, and we've got to transition that into renewable energy in the next few years. And so we need to make our use of computers more efficient, and also not do things that we don't need to do. I mean, I think that and make sure that renewable energy is the source of what we do. So power consumption is important, and obviously performance and power consumption are linked. If you're just wasting your CPU cycles doing things slowly, then it uses a lot more power. I highly recommend this paper. It's not at all well known. I could do a whole. I'm thinking I might actually do a kind of papers we love talk on this particular paper. This is a fascinating paper where they basically take a problem of basically image processing, video conversion, and work out exactly how to implement it more efficiently. So first of all, they just implement it on a CPU, and then they vectorize it, and then they start building specialized hardware to solve the problem. And you can get a 10 times performance increase just by vectorizing it and using the hardware more efficiently. But then there's other factors of a few hundred over that on top if you build specialist components to actually solve the specific problem you have. And that's going to be a difficult problem for us to solve. We're not used to building custom hardware to solve problems. We have to. We don't have programming languages that easily map to this kind of problem. This is, kind of a research area, and I'm going to talk a little bit about some of the issues involved in that. But what we can do is, we can use the hardware we have now that's more efficient and more performant. So all modern server CPUs have vector processing in. So things like AVX 512 was actually an Intel GPU design that they built into the CPU instead. And that you can get, as I said, factor of 10 performance on that is definitely entirely possible. GPUs and FPGAs are things that like many computers have and you can use, and are much higher performance for the right kinds of algorithms. But our programming languages that we use don't actually like natively generate these things in general. And if you program for GPU, it's like you have to use special toolkit chains and things like that. Juan Jose is going to talk at 1:40 about this, which is really exciting talk about just making Java just JIT compile for GPUs and FPGAs, which is, I think, a really, really exciting breakthrough. This is practical research that actually works, and you can use now, which is really exciting, I find. And you can get factors of 10 or more in performance just by doing this. But this is something that we all should be thinking about, in terms of language design and what we're outputting. JIT compiling is a great solution for this, but also we need to actually just think about it when you're thinking about programming languages, like why don't our programming languages natively support these platforms? Because they were all designed, for the PTP11 back in the day, and we haven't really rethought much about this. There's a whole lot of handwritten vector code now. There's some amazing projects showing what can be done, what kind of speed up. There's this SIMD JSON project, which I love. It's like Daniel Lamar's done a load of work on performance and kind of obsessive about using AVX 512 in particular, which is a kind of quite fun instruction set, to do actual practical things. So JSON parsing is not something that when you think of vectorization, you think vectorization, you think about numerical computation type things. But actually it turns out lots of problems, especially with the new instruction sets that we have, can actually, these things can be used to solve all sorts of perfectly normal things, but the programming model is kind of weird and interesting and difficult and not something that many people do. And we don't have general purpose kind of software tool chains that will generate this. This is handwritten code with intrinsic assembly operations and directly written assembly and other kind of horrible things to write. We really ought to be doing better at making this actually accessible. The Julia programming language for numerical computation has been doing really interesting work in exploring this space as well. I think that's another area that's really making progress in actually putting this in people's hands and making it usable. Another thing that we've been doing a lot recently, and we haven't kind of thought of as a thing, but is very much as a thing, is using programming languages to output other programming languages. I work a lot in the cloud computing space, and with things like Kubernetes, we deal with a lot of YAML, and no one likes writing YAML. So we've been starting to develop frameworks that are programming languages, particularly TypeScript-based, such as Pulumi and JK, that basically output as their end product YAML. Because then you can just write a program with abstractions and output YAML. There's a great talk about Pulumi by Joe Duffy from QCon New York, if you're interested. The same things happen with hardware. So there's the Chisel programming languages are basically Scala, but designed with a set of libraries to output hardware descriptions. It's being used by a lot of the RISC-V processors. Again, you can parameterize and write abstract functions, but then the output of this is then gates, which you convert to Verilog and output into hardware. Really, this kind of form of hardware design has been happening for quite a while. TensorFlow, again, is basically a set of libraries for outputting computation graphs for ML, and PyTorch and TensorFlow, and those are basically using Swift and Python as ways to output basically computational structures, which are basically languages. And language technology is just ending up everywhere in the kind of stacks we're using. So it's something that, if you look at things like TensorFlow, it's not I'm writing a program. It's right. I'm writing a program that generates code, but it's and so there's this kind of level of indirection we have, and this turns out to be essential in terms of optimizing that code and outputting it to different backends and different hardware, and different TPUs and GPUs and those types of things. The small is really important too. Servers are kind of interesting and fun, but there are ARM is shipping 20 billion chips a year, and many other people are shipping microcontrollers. These have turned into like actual normal 32-bit RISC machines that are sort of recognizably as performant as slow computers a few decades ago. And there's a lot of people working on really fun problems like scavenging power from the environment, picking up solar or RF or something to program really, really low power machines. There are projects that I've heard about that are thinking of shipping billions or trillions of microcontrollers for all sorts of projects, really, really exciting projects. But we need to program these things, and we can't, historically, these were programmed in C or assembly directly, and like we can't program billions and billions of microcontrollers in low-level languages. We really need high-level languages. But these are kind of, these are weird environments with weird things. So I'm really excited for Ron's talk later on 410 and about TinyGo. So Go is a programming language that I program in a lot, and it's had great success in the cloud and in containers and things like that. But it's also turns out that it's also a great language for programming microcontrollers. So come to Ron's talk. Like servers, microcontrollers are doing all sorts of interesting new tasks. Encryption is something that microcontrollers have always had a problem with. I remember Chris here did a talk many years ago about the problems involved in that. But we're now adding hardware accelerators for doing encryption and for doing ML and running ML models and things like that on microcontrollers. And I've talked to people who are building toys who want hardware-supported encryption on the microcontrollers they're using in the toys, because the toy has to talk to an app, so the app can control what the toy does, and you can't actually talk to something without encryption and security if you're a sane person anymore. People want to run AI models, and it's possible to run AI models on really, really tiny, very low-power microcontrollers that just do things like, say, voice recognition and things like that. There's a whole lot of work on 1-bit AI models, which is kind of taking the numerical precision down as low as it can possibly go, and then you can actually run them on really kind of small, very, very low power controllers. And so there's a load of the same trends in microcontrollers that also, again, we need high-level programming languages and frameworks to work with these things, because you really don't want to write these things by hand in assembly. WebAssembly has got a lot of hype. Why is it different from other platforms such as the JVM and things like that we've had that can run everywhere? I mean, I think obviously the huge thing about WebAssembly is it ships in the browser, and suddenly we can run lots and lots of programming language in the browser in a way that doesn't involve compiling everything to JavaScript, but is actually a native backend. And pretty much, this is kind of, since the JVM was removed from the browsers a long, long time ago, this is like a point at which we can suddenly run language we like in the browser, and this is causing a load of innovation, and loads of interesting new platforms are being built. And pretty much every programming language now has a WebAssembly backend, so you can write in any language you like and run it in the browser. And it's a new kind of open process, and it's a new open design, and it's unlike the JVM, it's not designed originally for one specific language. It's designed to be quite general purpose, and there is people working on extensions for it and building new platforms for it. So Cloudflare's web workers is one thing that's really kind of interesting. Is you can just run code on the edge in a CDN using WebAssembly. So Colin's going to talk later about building your own compiler. I think compilers are great fun, and if you're interested in languages, it's great fun to learn about compilers. And Consort's going to be really, really hands-on and interesting, and you're just going to learn how to do it yourself, and which you can also understand how WebAssembly works from that. So I think it's going to be highly recommend coming to that, 255. Another thing that WebAssembly is, the kind of dream of WebAssembly, it's a really hard problem, and it's something we haven't ever done before, is to have every language interoperate by converting it to WebAssembly and being able to share libraries written in any language. Now this is hard because languages have different things. Python doesn't understand like the linearity restrictions in Rust. Every language has its own garbage collector or doesn't have a garbage collector, and things like ownership are really hard problems. The JVM kind of got around this by forcing every language into one model, so that there were extensions to this over time, but everything used the same object model and garbage collection model. For WebAssembly, the dream is to actually make it so that you can interoperate all programming languages together. And we're way away from this, but it's a really fun problem in language design. It's a really fun problem. There's a lot of work going on this, and there's kind of dream that we can actually make it so that you can just pick and choose a library that you want to use from one language and use it with another language totally seamlessly is a kind of a really exciting possibility in language technology. And I think that we're years away from this working, but little bits of it are going to start to happen gradually, and we're going to get towards that. I think it's really exciting opportunity with languages. Security and safety is really important. Fuzz testing is something that has kind of broken into the mainstream gradually. The first really successful fuzz tester was called American Fuzzy Lop, which is a kind of very cute rabbit, released in 2013. And it's now available as a service. There's Microsoft and Google and various other people have fuzzing as a service for open source projects and commercial projects. There's tools such as Semler, which GitHub bought last year, which isn't a fuzzer, but it analyzes security issues you find and finds other ones in your same code base or different code base, which is really exciting. Security testing used to be manually people trying to hack things and see what happens, but now we've got this tooling, and this tooling is working. If you look at the number of CVEs filed, it's gone up a lot in the last few years. CVEs are not necessarily the best measure of anything, but I think automation has just been finding a lot of these CVEs and better tooling. And if you look at what kind of issues they are we've had a lot of memory safety issues, buffer overflows, heap buffer overflows, use after free, uninitialized. These are all memory safety issues that a large number of which come from C and to some extent C++ code. This is effectively, something like 70% of all the security issues filed as CVEs are memory safety issues, which is kind of ridiculous given that, we haven't released a programming language that's not memory safe for maybe 20 or 30 years. We have all this critical infrastructure written in C. We've just got to replace it with stuff that's written in a language that's more than, is less than 20, 30 years old. Any language, doesn't really matter. So memory safety is this big security problem that's just kind of, the languages, we already know how languages can help. You can literally just use JavaScript and you're memory safe or anything, it doesn't matter. You don't have to obsess about Rust or new languages. You can use anything to be memory safe. But there are more problems than just memory safety. I think safe concurrency and concurrency that doesn't have bugs in is really important. We're writing a lot of programs that do a lot of concurrency. We're doing a lot of asynchronous coding and things like that. And if you've done that, you discover things like deadlocks and race conditions and things like that, which are just kind of really annoying. It turns out that languages can help us with problems like that. And 525, Sophia's going to talk about a language you probably haven't heard of called Pony, which is a really fun new language. And she's going to talk about some of the type issues and safety issues about having a massively concurrent language that hasn't got any of these kind of concurrency issues. And it's a really fun language, also been quite influential in terms of influencing other languages. And it's being used in quite a lot of high-performance applications. Let's use our type systems to avoid these other types of issues, many of which are security issues as well. Once you get past all the memory safety issues, you find all the other security issues, and race conditions can often be turned into security issues as well. Languages are appearing everywhere. This is the recent RedMonk language rankings. You can see we have a lot of programming languages, and this is only the most commonly used ones. Why have we got so many programming languages? Well, I mean, we have even more than that. There's actually thousands and thousands of programming languages. I mean, languages are our tools as programmers. And you know, if we try and do different things, we build different languages to do those things, and that's really, really great. And we've been trying to do more and more complicated things and complex things. We've expanded the scope of the kinds of problems we're trying to solve and how easy we want these things to be. And language turns out to be an essential tool to handle complexity. I mean, I've talked about the things around ML and configuration and things like that. Language is incredibly important. And we want to start doing things that are more complicated. We want to, you know, we started doing things like just IDEs and having languages, you know, having our editors understand languages. Now we want to do things with more things with our languages, with code, such as analyze them, find bugs, like great things like, you know, there's tools that reduce errors that you find, test case errors that your fuzz tester finds into understandable examples and things like that. We want to manipulate code with code. It turns out there's all sorts of you know, things like that we want to do. And the languages we have are not necessarily that great for doing that with. And so a lot of the experimentation has been in things that we need to do. What's coming up next? There's a blog post by Graydon Hoare, who is the original author of Rust, which has a bunch of really great ideas. I recommend you read that. I think that there's, if you're a C++ programmer, undefined behavior is something that causes a lot of bugs. Undefined behavior is this terrible concept that originally kind of existed for good reasons, like we don't know what your machine does, so we're going to say your language can do whatever the machine natively does because that'll be faster. But it turns out that now undefined behavior is something that compiler writers use to screw you over and basically say, well, if you write this code, which looks perfectly reasonable to you, it's undefined and therefore we can do anything, so we will just delete your code or do other things that basically cause terrible bugs that you won't understand, and we won't tell you about this because we're just doing it for performance reasons, which is has been a total design disaster in programming languages, and I think it's something that we've really got to get rid of because it's going to cause more and more issues, and it's just not helpful. We actually need to be able to reason about what code does and think about code, and I'm a big fan of trying to make formal reasoning tools more accessible to people to understand their code better, but you can't reason about code if it's undefined behavior because it just doesn't actually mean anything. So I think that's something that we've really got to change. We've got to make language technology more accessible. I think it's really important that people can build languages into their tooling, and this is something that I think we've actually built these big projects like LLVM, which are kind of great because they are accessible in one sense in that you can build them into your technology. They're designed as libraries. LLVM was built as a set of libraries rather than a specific tool chain like GCC, and that was great, but it's big and complicated, and it's actually kind of difficult to use. I think you can actually build languages and compilers that are really small and simple to understand, and I think that you know, learn how to build a WebAssembly compiler later. You'll understand that it's not some big magic thing. It's something that is actually small compilers and small tools are actually still possible in the language space, and we've kind of neglected them a bit, and I think we need to go back to those. And small languages, so TinyGo is an example as well, but small languages. I've always been a big Lua fan. Small languages are great, like small languages that are understandable and you can embed them into other projects and things are really great. Safe languages like Pony are a really exciting frontier. I think Rust has reinvigorated everyone's interest in safety and the kinds of, let's actually make it possible to write things that you can tell are correct, because there's nothing worse than code that actually doesn't work right. And let's work with modern hardware. I think the Tornado VM talk later is really important because hardware has changed, and we've got to work with these things, and we've got to, actually change our mental model of what hardware is like. The bare knuckle performance track in this QCon is always really good from that point of view, just people who are obsessed by what hardware does. But I think all programmers need to kind of understand a little bit more about hardware and how hardware is changing. And I think that learning about those orders of magnitude difference in performance that you can have is really important. The Tower of Babel, I think, diversity in languages is diversity in ways of communicating and thinking, and it can be divisive, and I think that's what the biblical story was about, people not being able to communicate. But I think the great thing about programming languages is that they shape the way we think, but we can learn lots of languages, and we can understand different languages, and we can learn things from them. I think my kind of a long time ago, I learned Haskell, and it was very influential in how I think about things as a programmer, and I thought it was incredibly useful. I have never written a production line of Haskell in my life, but it as a thinking tool, it was really, really valuable. And I think there are many programming languages like that, which help us think about different ways of solving problems. And I think it's really, really important that we go out and learn programming languages and think about, why is TensorFlow so different from other things? Why are we doing these new things with languages? What would a native GPU programming language be? Why is it so difficult to work with these things? I think that we need, there's so many things going on with programming languages now that it's a really, really exciting time. And there are languages like, language communities are becoming very friendly. I mean, Rust is one of the great examples of a community that's grown up through open source and open participation and open specification. That's not it's not a sitting there with a kind of commercial background or anything like that. It's sitting there, but there are many other languages like that too. And you can join in and you can participate and you can shape the future of programming languages in a way that was difficult a few years ago. And so I think I'd really encourage you, if you're interested in that, to kind of find a language community or language communities and participate and understand what the problems they're trying to solve are. And these are hard and interesting problems, but they're languages give us leverage, and if you can build tools that everyone can use that makes their life better, it's an amazing thing to do. And so I'd really encourage you to think about this, and hopefully you can get some inspiration from the talks in the track today. So thanks very much. Any questions, thoughts, comments?
I have a question.
Yep.
My question is, what are some of the other languages that are not going to be participating in the conference today that you think are especially interesting? Who are some of the languages you would have liked to have attended that you were not able to make?
There were lots, actually. When I did the language track at QCon New York, we had a great Rust talk. We had, and I encourage you to watch the videos, a great talk about making NPM safe, about security in JavaScript, which was really, really amazing. I think there's a bunch of my friends have become obsessed about Elixir, and Erlang and those languages are something that has a load of really different ideas that other languages still haven't adopted about. That I think we have a lot to learn about if you're interested in sort of the cloud native world and updating code. Most languages don't even think about the problem of updating code. There's a whole set of stuff about UX of deploying languages that Dark is exploring. Dark is really, really, really early stage, but it's kind of, I think it's something that I'd like to spend more time on. There were a bunch of people who couldn't make it to speak about, the whole area of interop with WebAssembly, this project called Soil Project, which has just been set up recently, which is all about how we're going to build tooling to effectively do multi-languages with WebAssembly. There's a whole bunch of, there's a language who's so new, his name I've forgotten, which is a bunch of the Pony team are working on at Microsoft Research, which was announced recently. Again, with Microsoft doing a lot of work on safety in languages.
Language that's sort of a Rust, language to generate Rust or something like that?
Not that I know of, but I think we were going to have a talk about the new stuff that's going on in the OCaml area, which is an ML. There's a lot of work going on in ML they're trying to do stuff that's really different. Yeah, there's kind of a lot. It's actually there was a whole bunch of talks that I really wanted to have that we couldn't have in the track. So another time.
The other side of I found myself over the last year or so doing a lot of really small DSL languages. You didn't really mention that.
Yeah, I should have. I think small DSLs are something that people keep coming back to, and I think that I kind of concentrate on kind of the sort of bigger language use cases, but small DSLs are and ways of basically helping people like express a problem that's very specific to that problem are really important. I think part of the reason I didn't was I've kind of been recently interested in the whole kind of let's use TypeScript for doing this sort of thing, which is a kind of recent trend, particularly in the spaces I've been working in. But I think that there's been this kind of let's do small DSL movement. I mean, Ruby and that community have always been involved in that, and the Lisp communities and Scheme and lots of people. So I think I do think embedding languages as the interface to how users experience your product is really a valuable thing to do, because it gives them a lot more power to actually do stuff that is just different and scriptable and programmable in a way that exposes the domain in a really understandable way. So yeah, I think that I should have covered some of that as well, probably. Yep.
Kind of looking at the graph that you showed for the different languages and the popularity, like to me it looks like it's almost as if things are getting more fragmented. So are there certain areas in languages where things are consolidating in some sense?
It's kind of interesting because those numbers are based on kind of cumulative lines of code, so they kind of move quite slowly. But I think that one interesting thing is that some programming languages have been adopted into lots of kind of different new areas. I mean, Python has been amazingly resilient in the kinds of things that people have done with it. It's gone from being a web programming language and a teaching language to a language for ML and big data, which is an unusually big transformation for any programming language. It's proved to be very adaptable in that way, even if in many ways, as I said, it's being used in kind of weird ways in ML. It's like not really writing Python. You're using Python to drive other things. So it's kind of, but that's been adaptable. JavaScript, ever since it kind of broke out of the web in Node, has really become a very universal and adaptable language for all sorts of problems as well, and is, obviously is like, very popular, and kind of like the use cases for JavaScript and TypeScript and other variants of it are very broad. So yeah, languages do kind of change in those kinds of ways, and they do adapt, or some of them adapt, some of them don't adapt, I guess, as well. Some of them just get stuck in niches. It's interesting to see the sort of whether things like Kotlin and Swift will break out of the single platform thing. I mean, they're both languages that people like, but their communities are very rooted in Android and iOS, and it's hard to see whether those will break away or not. I mean, I think Kotlin's showing some signs of becoming a broader language. Swift seems to have kind of stalled in that at the moment. So it's a huge investment to build a language. It takes decades and a lot of work, and building community and libraries and everything. It's to build a truly successful language costs hundreds of millions of investment, which you often kind of don't really see. And some of it's people's time they're giving away in open source. But some of it's like real, hard money. If you look at the amount, like say, Apple has spent on Swift or Google spent on Go, it's a lot of money. Chris?
Justin, in infrastructure software at least, we've seen a swing from scripting languages, kind of Perl to Ruby to then Go to then everything's being rewritten in Rust now. Is that an oscillation thing, or is that a direction of travel? Are we going to see a renaissance of scripting languages, and if so, what do you expect that might look like?
I think that it's really fascinating, because we had swung so much in the other direction towards kind of interpreted languages, and I think it's partly driven by tooling. So like Rust picked up LLVM, and you have a great compiler infrastructure just off the shelf. I think it's partly a reaction to people have gone back to wanting types, because type safety is just, it makes large-scale program refactoring and those kinds of things just easier. I think part of it's that it took languages like Java quite a long time to adapt to the sort of container world of restricted memory and not owning the whole machine. I mean, even just sort of basic things like the JVM knowing about C group memory limits and things like that was just a barrier to use in those areas. Some of it's fashion. There's definitely a lot of fashion in languages. I mean, Go, Docker was very influential in actually making Go break out beyond Google, so I think those things can't be ignored. But I think we're going to stay that way because performance matters more. And also, I think partly Go showed that you could have a compiled language that was still compiled in a few milliseconds, and therefore you didn't have the kind of wait an hour to compile C++ build cycle, and that developer friendliness was actually what people wanted from interpreter languages. It was just like instant there, and Go just showed it was possible, and that's been incredibly influential in other languages. Like short compile times are now something that you can't, once you've had them, you can never go back. We're out of time now. Thanks very much. Please come to the other talks and try. They're going to be great fun. I'm really looking forward to them.